morning, good morning. We start today on page 53. So let's just look at a few other things before we dive into the new stuff on 53. So first, we'll have our look at the quiz, or sorry, at the calendar. So last class, we looked at some velocity functions for our zombie race, and it turned out that to find the total distance traveled, looking at a graph of velocity, we needed to find the area under that velocity curve. So that was the big result from last time, and that's written down again at the start of today's material. Today we talk about something called the definite integral, and the rest of this week we're just talking about integrals and something called the fundamental theorem of calculus, just in time because we're about to end Calc 1, so we're getting to the fundamental theorem here, and pretty much all this stuff in Chapter 5 segues very nicely into Calculus 2, which I think a lot of folks are heading to after this class. Bubba. This stuff will be on the final. All of this stuff will be on the final. Going until Friday. That's the last day of new material. Monday is our review day. Okay. All right. So currently you are hopefully thinking about Project 8. Remember, this was just the reflective project, so not a math project per se. That is due anytime by the day of the final exam. And this Friday is our last quiz. Any questions on anything there? Okay, so that is that. I sent an email on Friday about the videos for the sample test problems for the final exam. Let's just make sure we can find these things here. So there are some sample test problems in the packet. I don't know exactly where they are, 50 something, I think. There we go. So on page 58, you'll find some practice problems for the final exam. And somebody had asked me if I would put videos up on YouTube for these things, and I said, no, I don't have time. But then it turned out that 2 years ago, I did make them already, so they're up. Yeah, 2 years ago, right around this time of the year is when I first started making videos of individual problems, and so I was thrilled that I'd already done it. So those are the sample test problems. They're start on page 58, and if you go to YouTube and you know what you're doing, it's very easy to find a video for any problem. This one is 201 sample tests 4, just to try to follow the pattern. It's our 4th test. And then problem 7, and if we hit enter, it should pull up the video on that problem. There is a playlist with those problems all together. Any questions on that? Okay. Let's also talk about registration. So we just got an email from Cher. Cher is the second from the top person. We have President Bob, and Cher is second. And so she sent this email to all the employees here. Talk with your students about whether or not they have registered for next semester. So if you haven't registered because you have a hold on your account, and it's a vaccination hold, then we want to make sure that you know how to get that hold removed. And the way you get that removed is by talking to the folks over in Health Records. If you don't know where Health Records is, you go to GCC's homepage and type in Health Records, and it will tell you exactly where it is. So there's a real nifty search bar up here that works quite well. Let's make this a little bit smaller. And if you type in Health Records, it is located in the north building on the ground floor, G07. So underneath the bookstore. Thank you. All right, so that's that. And then there's another kind of hold that is very common for folks to have, and that has to do with financial aid. And if you're uncertain about your spring financial aid, go ahead and talk to the people in the financial aid office. In particular, Amy and Linda can help, but really anybody there can help. And if you don't know where the financial aid office is, you go onto the homepage and you type financial aid. It's on the core and the first floor. So we're encouraging people to register. At the moment, our spring registration is, our numbers are a little bit lower than they were 1 year ago at this time for last spring registration. And we're just trying to get a good sense. I mean, it's difficult to plan without having a good sense of exactly how many students we're going to have here at GCC. So if you are able, we'd encourage you to register as soon as possible. Any questions on that? And the bills for the spring term are not due until like mid-January or something. So you could register this month and not have to worry about paying for it until January. Okay, so that's that. Okay, so then we begin on page 58. And, no, sorry, we don't begin on 58. Where do we begin? 53, thank you. So we begin on 53. And we've got a lot to do today, so let's just jump through this, quickly review the stuff we did last time. Number one says the goal of this chapter is to take a given function, y equals f of x, and find the area A between the function, the x-axis, and the two vertical lines at x equals A and x equals B. So the area that we're interested in is all this stuff in here. And it is trapped on four sides. It's trapped on top by the curve. It's trapped on the bottom by the x-axis. We're always going to count area starting or ending at the x-axis, okay? And then a couple of vertical lines, x equals A and x equals B. Number two says there are some surprising applications of being able to find the area under a curve. In the last class, we saw area under a velocity curve gives what? Good. And I never know how many L's are in traveled. I usually just type it and wait for Word to underline it in red, telling me I'm stupid. Is that right? Is it just one? For some reason, I want to say either one is okay, but. So controlled with two L's is okay? Either way, it's okay. All right. Maybe I'll try to remember travailed. Thank you. Okay, we'll get to some other applications later, but for right now, we're just going to, if you'll go with me on this one, that we're just going to try to find areas under curve. That's going to be our goal for this last week of the semester. Area under a curve turns out is really quite interesting. So we're going to focus on that, and next semester we'll talk a lot about the applications. Oh, yeah, here it says in Calculus 2, and then it got hidden, but Leibniz's Revenge was the subtitle for that class. So let's take a look at 3. We had a curve, and I don't know why my rectangles are so dark, but they are, and we estimated the area under that curve by, in this case, there are 4 rectangles. Can you guys tell if those are left or right rectangles in that picture right there? Are those left or right rectangles? 1 vote for right, a couple of votes for right. A few more votes for right, good. So again, the idea is if you have to choose from 2 given points, and then pick one to determine the height of the curve, it looks like this one. The height of this box is dictated by the curve at the right-hand point, and that's true on each interval. Okay, and then we use left endpoints there. We could just as well use right endpoints. We could also use, well, what kind of endpoints do you see in this picture here? Sorry, what kind of points do we pick? Say if you're looking between this guy and this guy. Which of those 2 points dictates the height of that rectangle? Both of them? It's the midpoint, actually. It's neither one of those that determines the height. It's actually the midpoint. Go up to the midpoint, find the value, go a little bit to the right, a little bit to the left, and then back down to make the rectangle. You can pick any point you want in each interval. What's the point of this sequence of pictures here? Good. The more rectangles you take, the more accurate the area calculation is. That's great. So you can see when we used 5 rectangles, we have some space that's still white down here that we missed. We have some other space, let's see, sorry, we grabbed that space that we didn't mean to, and then we have other space up here that I think the first way I said it was right, and then I corrected it and made it wrong. So this guy right here is under the curve, but we missed it with a rectangle. This guy right here is not under the curve, but we grabbed it with a rectangle. So we have some overestimating and some underestimating happening. And the more rectangles you take, the smaller that error is. And in this last picture with, I don't know, like 40 rectangles, I can't even identify where the error is. I know that each of these rectangles has a little piece that's above and a little piece that's below, but the error is going to be pretty small by using just those 40 rectangles. All right, number 6 is a quick detour to talk about series and sigma notation. So a series is just the sum of a list of numbers, a sequence of numbers. So for example, 5 plus 10 plus 15, all the way up to 50 is called a series because it is a sum, right? Series S, sum S. And if you have a series, which is formed by adding a bunch of numbers that have a pattern that you can write down, then it turns out there's a short way to write that series. Instead of writing all of this stuff, we could just write this thing right here. So let's see if we can understand what that funny looking symbol means. So first of all, what Greek letter is that? Sigma, which is like our letter S, because you are summing things up. So sigma S, sum. And here's the idea. Every number in this list right here, 5, 10, 15, 20, they're all multiples of 5, yes? So then I could say that every term in that list is of the form 5 times some number. What's the sum number in the first term? Yeah, so this guy right here is really 5 times 1, and then this guy right here is really 5 times 2, and we can keep going, and the last guy is really 5 times 10. And so the way that we write that sum out using our nice little sigma shorthand notation is to write this stuff here. So that sigma means you're adding a bunch of things. 5k are the generic forms of the things you are adding up. What's the smallest value that k will take? Is 1. What's the biggest value k will take? Is 10. And so you can see going from 1 to 10. Have we seen sigma notation before? I don't think we talked about it when I did pre-calc. No. So just some vocabulary here. The 1 and the 10 are called the limits of the sum. And I realize that's a duplication of another word that we saw the word limit before when we were approaching, like on a curve. This is a different word, same word, different meaning. The index, that's the variable that you pick. It could be any letter. It could be K or I or J or anything at all, but it's called the index. And then the actual thing that you're adding up, that's called the summand, the things you are adding.
Does the K equals 1 mean you start at 1 or does it go in intervals?
You start at 1. We always go in intervals of 1.
You always do integers?
Yes. Yeah. So integers one by one at a time. Yeah, good question. Okay, so on the next page, it says the calculator can find sums pretty easily, and I've written out what I hope are some very clear instructions in here, but we're not going to be focused on that right now, so we're going to skip it. But if you're interested in getting the calculator to calculate that sum for you very easily, just see if you can follow those directions there. Correct. K could start at any number. You can see when you type this thing into the calculator, you have to put the 1, and if you change it and put a 2, it will start at K equals 2 instead. Yeah, K can start at any integer and end at any integer. Sure. Can you guys calculate that by hand? First number you're plugging in is K equals. Good. Plug K equals 2 into that thing in the parentheses. What do you get? So we get 11. So I'm going to put an equals. That whole thing is equal to 11 plus, because that's what the notation means. And then we plug in K equals 3. What do we get when we plug K equals 3? We get 18. Another plus. K equals 4, which gives me 25. Another plus. No more plus. I'll stop right there. Starting with K equals 2, ending with K equals 4. Nikki? It's always integers. Yes, that notation only works for integers. Yeah. Did I add it up right? I think that's okay. Abby, is that good? Okay. So number 8, we saw this really crazy, messy formula, and it's been a full weekend, and the notation is pretty intense. So let's make sure that we understand the funny notation. So what we did before was take our interval. We started the interval at A and ended the interval at B, and we chopped it up into a bunch of equal pieces. Do you guys remember the letter we used for how many equal pieces? It was n, was the number of equal pieces, right? And we wrote that last time. n was equal to the number of intervals or the number of rectangles. And so we cut that interval up into n equal pieces. And that gives us, actually, how many dots does it give us? If you have n intervals, how many dots are on that line? N minus 1? And plus 1. I knew if I waited long enough, it was like we were bidding on something. I just had to wait for it to get high enough. So there are n plus 1 dots on there. If you think about it, I hope it makes sense. How many little intervals are there? There are 1, 2, 3 little ones. How many hash marks? How many dots? 4. Right? So there's one more dot. Then, okay. And I think we can see that because this is 1 and this is 2 and 3, 4, 5 all the way up to n. That's the last one, right? Except what did I skip? I skipped the 0 one. So you can see n plus 1 up there. And then we had this funny little formula that told you how wide each of these intervals is, assuming they're all the same length. We wrote this last time. It was take the entire thing that you have to play with and cut it into n equal pieces. So b minus a tells you how much space there is total divided by n. Chop it into n pieces. I mentioned last time the notation gets very heavy at this point. I mean, it's not going to get, well, it'll get a little bit heavier. This is the heaviest that we'll get down there at the bottom. So we're almost there. But I recognize this is a lot of notation. And then what we did is we said, okay, let's go ahead and use, so in this one it says a right-hand sum. So let's draw a right-hand sum. So that's one right-hand rectangle. Draw another one in black here, up to the curve, over, and then left. So in that first interval, here to here, which point dictates the height of the rectangle? It was T1, the one on the right. And so you go to take T1, you plug it into the curve, right? So that's this f of T1, and that tells you the height of the rectangle. How wide is the rectangle? It's delta t, whatever that thing is. So taking f of T1 is the height, multiplied by delta t is the width. That's the area of the first rectangle. And then we move over and we do it again. Between T1 and T2, which is the one that gave us the height? T2. We go up to the curve, which means f of T2 is that magic height. The width is still delta t. F of T2 times delta t is the area of the second rectangle. And then we keep going all the way until the end, and it actually got cut off a little bit by my picture. Sorry about that. This should be f of Tn times right next to that last delta t. Okay, so that thing right there is called a Riemann sum. That's the guy's name, George Bernard Riemann. Your book might reference Riemann rectangles, named for the same person. And so we're going to use sigma notation to see if we can rewrite that long formula from up above. So here we go. Sigma notation starts with a big sum. And then there's a k equals down here. But before I figure out what k is equal to starting and ending, I'm going to try to write my general formula in the big blank space. So let's look at the terms up above here. Delta t times f of T1, delta t times f of T2, delta t times f of T3. Let's generalize that. What's the same in all of them? Delta t times f of, all that's the same, right? The only thing that changes is the little number on the bottom of the t. So actually there's one more thing that's the same in all of them, is t. I just need to put something down there to indicate that I've got something changing. What can I put down there? K. K is a good thing to put down there. So K is just going to be my little counter, tells me which one I'm on. For the very first term right here, how much is K? Is 1, f of T1. And the next one, how much is K? 2. And then K is 3. And you can see it's every one. We're going integers. So down here at the bottom of my sigma, K equals, what's the starting value for K? It's 1. And it got cut off, but we added it in. What's the last value that K takes on? Is N. Okay, so that right there is our crazy notational way to write down the sum of a bunch of Riemann rectangles to estimate the area under a curve. A lot of pieces, a lot of notation. Nikki. I think that for me, the k equals 1 indicates that we're talking about the first rectangle. It's the one that's black in that picture. And then k equals 2 is the blue rectangle. And we're just, every rectangle has a number. Yeah. Okay, 10. What can we do to get better and better approximations for the exact area under the curve? So let's send n to infinity, right? Instead of using 4 rectangles or 400 rectangles, let's use infinitely many rectangles. So that's what we're going to do. Number 11, full-fledged, hardcore, no messing around definition for the area under a curve. All right, forget the setup, but the equation is what I want us to look at here. This thing looks very familiar to us. 2 small changes. It's I instead of k. No problem. I equals 1 is going to give us the same thing that k equals 1 gave us. I equals 2, I equals 3, all the way up to I equals n. Fine. What's the only other small difference here? Yeah, we got the limit, so we'll take a look at that, but just in the red part. How does the red differ slightly from the purple? Yeah, I would just multiply it in the other order. Doesn't make any difference. Okay, so the new thing then is what's out front. This guy. Limit as n goes to infinity. Again, what does n stand for? It's the number of rectangles. So this is exactly what Garrett suggested. Let's let the number of rectangles go to infinity. And if we do that, using this theoretical infinitely many calculations, that thing right there is our way of giving meaning to the area under a curve. That thing right there is no longer an approximation, but what it is the exact area under this curve. Starting here, going over there, all this stuff exactly. We don't have any extra, we don't have anything under. It's a perfect answer. It is the perfect answer. It's the definition of the right answer for what's the area in there, okay? So it's a crazy looking thing notationally, but I'm hoping we understand the pieces. Even I'm not going to ask you to just like write that thing on a quiz or a test, but I hope we understand all the pieces that went into it. We cut the thing up into n pieces, find the area of n rectangles, and then at the end, send n to infinity. N is the number of rectangles. K is just this letter that is your counter. It's just the thing we're using to be able to write down, hey, just start going 1, 2, 3, 4, 5. That's our way of writing it down. Yeah, it's just a counter. Okay, 12. So as I say, this formula isn't something you need to memorize, but calculating area under a curve is something we'll do many times, a little bit this semester, but many times next semester. And we're going to want some notation so that we don't have to write down that whole thing that I circled there in black. It's quite unwieldy. So here's the new notation. It's super important in any future calculus classes you take. Calc 2, Calc 3, Calc 4, anything you take, you will see this notation. Here it is. We're going to use those funny symbols right there to denote the area under the curve between A and B. It's the area between the, yeah, for all of this, the function has been non-negative, I think. Yeah, I didn't say it out loud, but we're assuming that the curve is up above the x-axis, but it does, although anything below the x-axis, this thing will count as having a negative area. Yeah. Okay, so, let me just draw a quick picture here. You guys had the zombie race last class, and I forget who it was. It might have been Planck, but his strategy was, am I getting it right? Was that Planck? All right, so that was at t equals 5 hours, and I think his top speed was 3 miles per hour. And let's just go ahead and give a name to this function. So let's call this one f of t equals, so maybe this is just a regular old parabola. It's not going to match perfectly, but it should be enough to get the idea. I'll do something like x minus 2.5 squared. Just to make up something that kind of looks like that. Why is the minus 2.5 in there? Shifts it to the right. So just a regular parabola shifted to the right. And so I guess what we're saying here is that if you wanted to find the exact area under this curve, going out there to t equals 5, let's see if we can write it down. So here it is. It's that funny kind of curvy symbol. The a and the b are the left x value and the right x value. What's the smallest t value in this case? 0. What's the biggest t value? It went out to t equals 5. So we go 0 up to 5. Everybody see those two numbers in the picture? Probably you shouldn't because I didn't write them both. 0 to 5. And then the next thing that we're supposed to write is the function, f of t. So what is f of t? It's that thing right there. I'm going to put t minus 2.5 instead of x. Squared. And then the last symbol apparently is t. So all of these symbols here indicate that we are finding the area that's shaded in red, the exact area. Not approximating it with rectangles, we're finding the exact number, the perfect number with no error. And it also happened that because that's a velocity function, what physical meaning does the area have? It's the distance traveled. Joe. Good. Yeah, it's a good question. So let's start looking at the kind of comparison between the two symbols. So right now I'm looking at this thing, just trying to see where the pieces went. We introduced this really funny looking notation to represent the area under the curve. Let's see if there's any rhyme or reason here. So as Joe points out, there's a dt inside of the new symbol that sure seems to remind us of the delta t that was over there. That delta t, remember, was just the width of each of the intervals. And then the next piece I have is an f of t. Well, that looks an awful lot like this f of ti here. And then there's this integral sign. Sorry, then there's this sigma. What does that kind of look like on the other one? It's that funny looking symbol that maybe you've seen before, maybe you haven't. But if you had to pick a letter that symbol looks like in English, what letter would you say? Maybe it's a stretched out S, like you kind of have to use your imagination, really stretch it long. If you've ever looked at any of our founding fathers, like the historical documents, like if you've seen the word Congress written in, like old, it had S's that looked just like that. So, and then finally, this limit as n goes to infinity. Well, it doesn't appear in here, so it must be buried inside of that funny symbol there. Okay, and then there's one other thing. The A and the B in the new funny symbol that tell you your start and end points, they don't appear in the picture on the right-hand side. It is what it is. So Joe points out this dt and the delta t, and they're supposed to remind you of each other. The delta t was the width. dt is supposed to remind you that you're multiplying a width by the height of the function, f of t. And then there's some vocabulary down here. So the symbol that we just wrote down is called a definite integral. The numbers on the integral sign are called the limits of integration. There's that word again. Again, not to be confused with the limits that we saw where we were approaching some point from the left and the right. And then the function is called the integrand, just like we had a summand before. Okay, so lots of background stuff. Let's see if we can now actually do something with all these new symbols that we've built. Defining areas using that formula is tough, but your calculator does a pretty decent job of it. So let's see if we can find this integral from 0 to 3 of x squared dx. So before we use the calculator, can we do a real quick sketch? So that symbol represents the area of something. So first I'm going to draw. What function am I going to draw? x squared. So we draw our y equals x squared. What's the starting x? What's the ending x that's going to trap our area? 0 and 3. So somehow the picture starts there, goes over to here at x equals 3. And then I'm going to go up to the curve. It hits someplace over there. The origin is the other point. And do you guys see the region that we've created here? So it's under the curve, above the x-axis, always between the curve and the x-axis. So this right here is the area that I'm interested in finding. That area is what this symbol represents. So all those symbols mean what is the area in there. So before we let the calculator help us out, I just want to get a real quick estimate for what that area is so we can at least know what kind of a number to get or to expect on the calculator. I'm going to draw a line connecting the two green points. Straight line. Is that line going to be under or over this curve? It's going to be over. Can you see what nice shape you could very easily find the area of without the calculator? Is that triangle. Okay, go ahead, find the area of that triangle. So the area of a triangle is half of the base times the height. Half of, what's the base? It's 3. What's the height? It's 9, or 3 squared. So this is 27 over 2, which is 13.5. Is the true area underneath that curve more or less than 13.5? It's going to be less because that curve was, sorry, the line was above the curve. So I'm expecting some number less than 13.5, but not that much less. So if I get, for example, the area is 2, I'm going to kind of question. If I get that the area is 15, I'm really going to question that. So at least we have some very, very rudimentary ballpark idea of what the answer should be. So a couple of ways to do this on the calculator. It's written out here. So the first way is to type in y equals x squared. So let's do that here. And then it says make sure your window includes the part between 0 and 3. So just the standard window, zoom 6, should be good enough for us. And then once we've got the picture up there, it says go to calc, which is second trace. And we're going to choose this symbol, the symbol we just saw. That funny looking elongated S. It's there in number 7. So scroll down or just hit 7. And then look, it says lower limit. It's using the limit, the word that we talked about. So what was the starting x value? 0. So type 0 and hit enter. What was the ending x value? 3 and hit enter. Oh, look at how nice that is. And the area is equal to 9, which seems perfectly reasonable. We got 13.5 for the triangle, so this is a little bit less, but not significantly less. And that's it. So that's kind of cool. So the one downside with doing that, so it is a nice picture there. If I were to do it again and go say between 3 and 11, right? So it's just like picking up and then going to the right. And if I hit enter, it says you're an invalid. It's so mean. That's not what it says. So why can't I do it? It's because the window didn't capture that. So if my window, let's quit there. If I send my window out there to 12, for example, as long as 11 is in the picture, then it should be fine. So we'll graph this thing, and then I could go between 3 and 11. 3 and 11. It's going to be a little bit dissatisfying in that a bunch of the shading is happening off the top of the picture. So if you want a better picture, you can change your Y max, but the calculator doesn't care. It just needs the X's to be on the screen. So it turns out that area is 434 and 2/3.
It's kind of weird though, because none of the other things be on the screen.
None of which other things?
Well, like if you're doing like different outputs.
Is that true? Let's see. So what if we check the first one, this value? So let's pick a number that's off the screen. 700. Yeah, the other ones, like 0, like you did have to trap something that was in the screen, right? You couldn't go off the screen with the cursor.
It doesn't generate it until you look at it.
That's right, and it's only generating the part that we see here.
Why does it why?
Yeah, I don't know exactly what the algorithm is that the calculator does, but apparently it treats the x's and y's quite differently. Mm-hmm. But it doesn't have any problems with the range not being seen. Yeah, don't know. Oh, but speaking of programming, let's go here real quick. I just happened to see this morning. But what are these things called? Google Doodles, yes. So today is, you can see it there, Ada Lovelace's 197th birthday. I don't know if you can tell, but there's all these kind of early computing devices gradually getting to the, oh look, they even got the, from that commercial that I see like every 5 seconds. So, and anybody know what this, what is that supposed to be? Relative to, yes, it says Google, but relative, what is the image of relative to the early days of computing? Yeah, it has to do with programming. I think that's the early tape that computer programs were written on. So apparently, this woman was the person who wrote the first computer program. She was using one of Charles Babbage's early computers, and it was just a counting machine basically. And she was the first person to write an algorithm that was specifically designed to run on a computer. So some call her the. She had some kind of cute nickname. I just glanced at it this morning. The Countess of Counting is what somebody, yeah. So she actually happens to be the daughter of the poet Lord Byron. It's kind of neat. All right, so coming back here. All right, so that's one way to do it. Turns out there is an easier way to do it that gets rid of all the need to actually have a good picture. So we'll do it here from this main screen. We're going to go into math on the far left. Scroll down until you see one that talks about INT, integral. So scroll down. You can see n deriv. We've seen that one before. And then the one right after it is this function integral. So hit enter. We're going to type the function. What was the function in this case? It was x squared. So just type it right here. Then we do comma. So I think the syntax is written out here. Then you do comma. Then you tell it what the variable is. The variable in this case is x. It's always going to be x for us, but you still have to tell it. Comma. And then you type the lower number, 0, 3, and you hit enter, and you get the same 9 that we saw before. And sure, it's cute to see the picture and actually get the thing to shade in, but if you just care about the number, this seems to be an easier way to find it. Because then you don't have to worry about finding a good window. Okay. So let's go to number 15. This gets at a question that Garrett had asked earlier today. This is what happens if the function is negative. So over here, looking at this picture, we've got some positive area in region 1, and then some negative area down there in region 2, and then some positive again in 3. Okay, so what does it mean when I say negative area? Area is always positive. It's true, but let's think about the notation that we have mastered now. Here, f of t2 was just this height, yes? And then f of t1 was this height going up to here. And they were positive numbers. But if the curve was below the x-axis, f of t1 would be a negative number, right? Like it's perfectly legitimate for some of these f values to be negative. And if I'm just blindly multiplying a width, which is always a positive number, times the function value, which could be positive, but it could also be negative, then some of these things will represent the area of rectangles as being negative, right? It's going to draw a rectangle that's below the x-axis, and it's going to find the area, but it's going to have a negative sign on it. So what that means is that we got to be really careful, depending on what the question's asking. If the question here says find the area under the curve, then we have to treat all 3 of those regions as being positive numbers. But if the question just says, what is the value of, let's write it out for this one, integral of f of t dt between, I can't see what the number is on the far right there. I call it 10. It's too small to read, isn't it? So that symbol right there, the integral from 0 to 12 of that function, again, the symbol means area between the curve and the x-axis. But it doesn't pay attention to whether those numbers are going to be positive or negative. So it's our job to understand anything below the axis will count as negative. So if I actually ask the calculator to find this integral, it would tell me the area of region 1, and it would also tell me the area of region 3. But what would happen with the area of region 2? It would end up being some negative number. So that symbol right there doesn't always mean the area. That symbol means the area if things are above the curve, but that symbol is going to treat anything below the curve as having a negative area. Okay? And in fact, we could make up a quick example here on the calculator just to see a number. Well, actually, we'll just do it here on number 17. But first we'll read 16. It says, just remember, the definite integral calculates a signed area, where the stuff above the x-axis has positive area and the stuff below the x-axis has negative area. So let's see if we can do this here in 17. So just so that we can see the picture, let's do this one on the y equals screen. So we're doing x cubed. Standard window is probably fine here, so I'll do zoom 6. Okay, and before we type the area commands, I want us to test our intuition here. We're about to ask the calculator to find the area between x equals -3 and x equals 0. So x equals -3 is here, and it's actually down here. Where is it? What number is down there? That's x cubed, so it's -27. So that's why I can't see it. It's way down here. So then what do we think, first of all, what kind of a number is this integral going to be? It's going to be a negative number because the area in here and going all the way down to there is all below the x-axis, and anything below counts as being negative. So first off, we're going to get a negative answer. We're going to get the negative of the area, whatever that is. But now I want to know, how does this guy compare to the answer that we got up above? Way up here, we did the area for x squared between 0 and 3. What did it turn out that area was equal to? It was 9. Okay, now we're doing x cubed between 0 and 3. It's the same 0 and 3. So the question is, do you think the area, forget the negative for a second, but do you think the area is going to be more or less than 9 for x cubed? I've gotten a couple of votes on either sides of the fence. So yes. So ignoring the negative sign. Yeah, that's the question. Yeah. So Bubba, are you saying bigger if we ignore the negative sign? Yeah. So yeah, I think I agree because the x cubed function is going to grow a lot faster and be way higher, and so it will have more space underneath it. So the area is going to be some bigger number, although it'll be negative. So let's get the calculator to help us out here. All right, so just because I like to see everything on the picture, I'm actually gonna change the window here so that I can see the bottom. So how about I go like -40 or something? Just so that, or maybe we don't do that. I'm in -40, y max 10. Okay. And again, where do we find the thing that will shade in the area for us? It's inside of calc. Down there, number 7. What number do we type for the lower limit? -3. You have to type the smaller one first. So -3, and the bigger number, 0. And so it'll shade in that space. And indeed, a lot bigger than the 9 we got before. and also negative. Now let's take a look at that. Does it shade it the same way? 7. So Joe is saying, what if we type it in this way? Oh, I'm going to change something real quick. I want it to shade it again, and I need to clear the shading that we had before. So I'm just going to do something silly so that it draws it from scratch. Okay, so let's try this integral going the wrong way, going from the bigger number 0 to the smaller number -3. I actually don't know which way it's going to shade. So all the ones we looked at before shaded left to right. I wonder. Yep, this one's left to right as well. So the same 20.25, but positive.
Isn't it what it's doing is it's taking like, it's doing like the integral f of 0 minus the integral f of 3, and now it's just doing it the other way, like opposite.
It is. So we're going to talk about why this is exactly the same number, but the opposite sign. Okay, so let's put an answer here. So is this equal to, is this area equal to 20.25 or negative 20.25? It's positive. The word area means positive. But can you guys write down some expression where the answer is negative 20.25? There's something we can write there so that we are getting that negative, like a signed area. What symbols go here? It's all that stuff that we wrote, the crazy S thing. Integral of x cubed dx from -3 up to 0. That's equal to negative 20.25. Okay, so I'm really hoping we see the difference. There's a big difference here. If I say area, the answer is definitely positive. If I say integral, that funny symbol over there, could be positive, could be negative, could be that there's some cancellation. Right? So there is a real big difference between these two symbols. Let's take a look at part B. Area between -1 and 2. So I'm going to come back here and I'm going to do zoom 6 so that I can have a brand new curve. So let's just see if we can type it in here on the main screen. So I'll go second calc and then 7. What's the smallest number? -1. And the biggest number, 2. And it's going to shade left to right. And I get 3.75. Is that the area? It's the difference of those two areas. That's what the 3.75 is. The integral sign treats anything below the x-axis as having negative area. This question said find area. This is not the right answer. And I don't even know how to get the right answer just from 3.75. We need to do something else. So what could we do? Separate them. Where's the place where the function goes from negative to positive? Is it x equals 0? So let's just do two separate integrals. I'm going to do zoom 6 so that it draws it again and clears that shading. So we'll do second calc number 7. The first integral, we could go from -1 up until 0. Am I expecting a positive or negative answer from the calculator? This will give me a negative answer. In my mind, I immediately change it to a positive answer. So let's write down something here. So the integral from -1 to 0 of x cubed dx turned out to be negative 0.25. The next integral we're going to find is going to go from where to where? 0 to 2. So we split it up based on where the thing changes sign. So we'll do the same thing here. I'll just ask it to redraw. And then we're going to go 0 to 2. So just the right-hand part of this is 4. Do you see why the answer was 3.75 when we just did it all in one shot? That's exactly what Ernie said. It was the difference of the areas. it did negative 0.25 and positive 4. Add them up, that's the 3.75. But what's the true total area here? 4.25. Everybody got a copy of the quiz answer keys from the semester? Okay. Yes. Go ahead. If we got messy decimals from the calculator, which you will for a lot of the functions, I would do the approximate sign. It turns out that these are nice numbers, that the areas here turn out to be nice, which is really surprising. It's not. I think it turns out that the process that it's doing, it's estimating. It's thinking about rectangles, but it's doing it in a very fancy way, and the error that it's getting is so insignificant that it's rounding to the perfect answer. Yeah.
This is a perfect. You took the area of an ellipse.
Yeah, you get something with pies. Yeah. Yeah. So we could even do that. Think about the equation of a circle. Do you guys remember equations of circles? And you guys write down real quick the equation of a circle whose center is at the origin. We'll make it easy. And let's make the radius of the circle equal 10. And you guys write the equation of a circle whose radius is 10. I want the radius to be 10. So maybe you remember equations of circles. X squared plus y squared equals r squared. That's the equation of the circle. So what Chris is wanting to think about is the area. So what's... It does. We're going to have to do some funny business. Yeah. What's the formula for the area of a circle? Pi r squared. So in this case, pi times 10 squared. So 100 pi, which is about how much? 14 point and then some stuff. Okay, so the calculator is not going to be able to give me the perfect answer here. The perfect answer is 100 pi. So what if we come down here? What letter do I need to solve for if I'm going to type the circle into my, I need to solve for y. So if we solve for y, what do we do first? So before we take the square root, subtract the x squared, then take the square root. So we'll do y equals square root of 10 squared minus x squared. Buy it? Is that going to be the full circle? That's just the top of the circle. Okay, so there's the top of our circle. I'm going to ask the calculator to find the area. What number? 7. Lower limit? Negative 10. Upper limit? 10. It's going to shade it all in. Possibly. $157.07967. Is that the area of the circle? That's half the circle. So if you double that, what do you get? 314 and some change. At some point, the change will be wrong. Yeah, good question. Yeah, the calculator is. Yeah, I mean it's using a very accurate guessing method, but
it's guessing like 20 decimals out, right?
Yeah, I mean it's going to be right for a long while the way the calculator does it. But you're right, it's an approximation. Okay, so I promised that we would do this one in 2 ways. So the first way we did it was to split it manually for us to decide, okay, I'll just bring the y equals x cubed function back here. what we decided was, all right, the left-hand part of this curve is below the x-axis and the right-hand part of the curve is above, so we're going to split it. Because we can't go from -1 to 2 directly, we have to split it -1 to 0 and then 0 to 2, right? So it turns out there is a way for us to just ask the calculator to give us the 4.25 in one fell swoop. And that's for us to tell the calculator, hey, make that function positive no matter where it is. What's the math symbol to make a function positive, to make something positive no matter what? Is absolute value. This is like one of the rare times you actually use absolute value. So if I go in here, and instead of having x cubed by itself, I insert the absolute value command. It's inside of math, and then over to the right once it's under number. And you can see ABS. So what will the new thing look like when I graph it? It's going to look kind of like a parabola. The right-hand side will look exactly as it did before, but all the stuff on the left-hand side that was negative will get turned positive, flipped up. Okay. And now if I wanted to find the area between -1 and 2, well, it's going to give me the right answer like it did before. But over here, it's going to find a positive, which is exactly what I want. So we do second calc and then 7. And then we go -1 over to 2. And it gives me the, oh, Chris. Yeah, it is definitely approximating. But it gives me the basically 4.25 in one shot. Instead of us splitting it, it's easier just to let the calculator make everything positive at the start.
Why was it? It was perfectly accurate the other way. Why is it now?
I don't know what the algorithm is that the calculator is using. It might be doing something called Simpson's rule, but it might be doing something more complex than that. We'll look a little bit at these approximation methods in Calc 2.
It seemed like it was the absolute value.
Yeah, somehow. Well, I don't know. What if I? The right answer is 4.25. So what if I just ask this one for -1 to 0? So it gives me that one perfect. And what if I ask it from 0 to 2? Yeah, so it can. So somehow, I mean, it's not splitting it up. When we ask it to split it up, it did both sides perfectly, but it's not smart enough to say, all right, let me do the two sides and then add them together. So it's picking some points between -1 and 2, a bunch of them, to try to be like a representative sample, like, you know, draw a bunch of rectangles, but somehow the way in which it's picking the points when we split it, it gives us this more accurate answer, and we get a little bit unlucky when we ask it to do it all in one shot. Yeah, so maybe there's some little problem around the origin.
Somewhere a while ago, I read an issue of like asked me to take a derivative of an absolute value. Like a really.
Yeah. So the absolute value function you guys have seen before. What letter does the graph of the absolute value look like? It's like a V. So what if I wanted to find the derivative of this thing here? I prime equals. It's actually two different rules. What's the derivative for all the uphill ones? It's whatever the slope of that line is, right? What's the slope of that line? 1. So if we're going to tell it two different rules, then we need to make a piecewise function. So if x is positive, then the derivative is always 1. If x is negative,
you always just split it up.
Split it. What x value did I not include? What's the derivative at 0? Doesn't exist. We've seen corners are bad for derivatives. Okay, so that is that. Next page. Let's try this one here. All right, so I'm giving you this crazy function e to the x minus 5x. So apparently the graph looks like that. Which of those two functions dominates if I were looking long term at this graph here? E to the x, right? E to the x is going to beat everything. So what does this part of the graph look like? All right, so yeah, right, subtracting 5x is going to be pretty inconsequential when x gets big. What does the left-hand part look like? That does kind of look like negative 5x, doesn't it? I thought e to the x was going to dominate. Yeah, what happens to e to the x for all those negative x's? It gets very close to 0. So it's insignificant, which is why it looks like a negative 5x. And then this piece here is where the two of them are kind of battling, and e finally pulls out the victory, right? Okay, so we want this integral, negative 2 to 2. So I'll just draw here on my picture. So negative 2 is this guy. Get rid of this here. So negative 2 is out here, and positive 2 is out here. And I'm looking for an area. So before we use the calculator, can you guys shade in the area that the calculator is about to give us? Negative 2 to 2. Okay, so negative 2. So we go up to the curve, and then we start shading. So it looks like I've got that kind of region there. And then where does it go when the function gets negative? Like, is it here? No. So on the other side, it's always between the curve and the x-axis. So as soon as that curve goes negative, you need to change where you are drawing. And it doesn't look like it gets the whole bottom part of this graph because it stops at x equals 2. So that right there is the area that we're about to find. And it's pretty straightforward to get this answer. So just use the calculator and let's see what it says. Okay, so we get that graph. And then we integrate from negative 2 to 0 or 2? I don't know. What does it say? Are we looking for area or not? We're just looking for the value of that integral, and that integral will give us some positive and some negative. Which one do you think wins looking at the red shaded region? Does it look like there's more positive or more negative area? Looks like the positive wins by a little bit, but we're not going to get some number like 10 or 20. There's some positive red area there. It's going to cancel some of this negative red area. Shade it in, and we get positive 7. Okay, so that's how much more you have of the positive part than the negative part. If I wanted the sum of those areas, what would I have to do? I'd have to split it, which means having to find where it's equal to 0, actually. It doesn't, I don't think it hits at 0. So you need to figure out exactly where it hits the x-axis and then split into two different integrals. Easier than that would be to do what on the calculator? Is that absolute value, because then it just makes everything positive at the start. Okay, so let's take a look at this guy a little bit more. And this is a preview of this thing which we're going to see next class called the fundamental theorem of calculus. It's like a wonderful way to end class in calculus, right? The fundamental theorem. Here is my question. We've spent a lot of time talking about derivatives. We've gotten quite good at finding derivatives of functions. For the next 4 minutes, let's think about the opposite process, undoing a derivative. Suppose that somebody took a derivative of some function and they got e to the x minus 5x. That was the answer to the derivative of some other function. So the question is, what's the other function? And you guys chat with your neighbors, see if you can find some function whose derivative is equal to this thing. Could be. Okay, so I think we've seen a bunch of folks come to the same answer. Whose derivative is e to the x? Is e to the x. Minus whose derivative is 5x, and a bunch of folks put 2.5 x squared. And that might look kind of miraculous to people who haven't seen this kind of calculation before, and that's okay. But one way to verify whether or not this is right is to do what with this function? Let's take its derivative. And if you take the derivative of negative 2.5x squared, the 2 comes down. Oh, look, builds the 5. X, new power, is just 1. Happens to work perfectly. There is a process for doing that, but at the moment, it's okay to just kind of make your best guess and try. Chris put a group, put plus 1,000 at the end. Is that right? It could be plus any number because constants disappear when we take derivatives. So there's no way to know what was out there, if anything. Here's what we're going to do. And it's totally fine to keep that 1,000. But what I want to do is ask you guys to, on your calculator, find f of 2 and subtract f of negative 2. So you've got your function in purple. I want you to find e squared minus 2.5 times 2 squared. That's f of 2. And then subtract the other number. Anybody get an answer? What is it equal to? 7.25. Do you have any more? Zero 0.81. Great. Okay, so we found this idea of an antiderivative. We plugged in 2 and negative 2, which were the limits, and we subtracted because I said, hey, just subtract these things, and we get that. And what's surprising about that? It's the value that we got when we asked the calculator to just find that shaded area. We get exactly the same thing with one fewer digit at the end. Okay, we'll end there. See you guys Wednesday.